Mathematics has always been more than numbers on a page. It is a way of looking at the world, a language for describing patterns, and a tool for reaching into the unknown. From the time humans first began carving marks into stones to count their animals, math has been our companion, guiding us toward deeper understanding. But what makes math truly fascinating is not only what we already know, it is what we do not know. The unanswered questions, the mysteries that still remain, are where imagination and discovery meet. Tonight, we begin a slow journey into these mysteries, letting each puzzle open like a quiet doorway to wonder. Think of it this way. Imagine standing in a vast library, stretching far beyond what your eyes can see. Each book on the shelves holds a solved problem, something humans have figured out about numbers, shapes, or patterns. But hidden between the shelves are empty spaces, books not yet written, problems not yet solved. These empty spaces are what we call unsolved mysteries in mathematics. They remind us that no matter how much we learn, there is always more to uncover. Some of these mysteries sound simple at first. Can every even number be written as the sum of two prime numbers? That is a question even a child might ask. And yet, no one has been able to prove it true or false. Other mysteries sound complex, involving ideas of infinity, dimensions beyond what we can see, or strange shapes that fold in on themselves. Whether simple or complex, each mystery invites us to look closer, to wonder if the world is stranger than it appears. These puzzles are not just games for mathematicians. They shape how we understand reality itself. For example, the way prime numbers are arranged turns out to affect how secure our online information is. The way infinite series behave has connections to physics, to energy, and even to the way time itself might unfold. Each mystery is like a pebble dropped into a pond, sending ripples far beyond what we expect. But perhaps the most beautiful part of mathematics is not the answers, but the questions. Unsolved problems remind us that human knowledge is always incomplete, that there are always doors waiting to be opened. They invite us to sit quietly with the unknown, to be comfortable with not having every solution, and to see wonder in the gaps. So as we begin this journey, let your mind relax into the rhythm of curiosity. These mysteries are not here to trouble you, but to soothe you with the reminder that the universe is bigger than any one mind can hold. Each unsolved problem is like a star in the night sky, distant, mysterious, and quietly glowing with possibility. Take a moment to breathe, to let the idea of mystery settle in. You are about to set into a landscape of questions that have puzzled the brightest minds for centuries. Some may never be answered, and yet it is in the asking that we find beauty.
In the world of mathematics, some questions sound so simple that it feels impossible they have not already been solved. Goldbach's conjecture is one of those questions. It was first suggested in 1742 by a man named Christian Goldbach. He wrote a letter to the great mathematician Leonhard Euler, asking about something curious he had noticed with numbers. His idea was this: can every even number greater than 2 be written as the sum of two prime numbers? Let's pause for a moment. A prime number is a number that can only be divided by 1 and itself. Examples are 2, 3, 5, 7, 11, and so on. An even number is any number that can be divided evenly by 2, like 4, 6, 8, 10. Goldbach's conjecture asks, if we take any even number, can we always find two primes that add up to it? At first, that seems easy. Let's check. Take the number 4. That's 2 plus 2. Both are primes. Now look at 6. That's 3 plus 3. Again, both are primes. How about 8? That's 3 plus 5. 10 can be written as 5 plus 5, or 7 plus 3. 12 can be 7 plus 5. It seems to work again and again. In fact, mathematicians have checked Goldbach's idea with computers for numbers as large as we can imagine, trillions upon trillions, and it always seems to be true. And yet, here's the mystery. Nobody has ever been able to prove it for every number. This is where the puzzle becomes so strange. On the one hand, the evidence looks perfect. No counterexample has ever been found. But on the other hand, without a formal proof, the statement remains just a guess. It is as if we are standing in front of a door that looks unlocked, but no one has yet managed to push it open. Why does this matter? Prime numbers are not just abstract playthings. They are the foundation of modern encryption, which keeps our messages, bank accounts, and digital secrets safe. The patterns of primes hide deep truths about mathematics and, in some ways, about the structure of the universe. If Goldbach's conjecture could be proven true, it would reveal that prime numbers are even more tightly woven into the fabric of numbers than we ever imagined. But perhaps the beauty lies in the uncertainty. For nearly 300 years, the greatest mathematicians have tried and failed to solve this riddle. It stands as a reminder that even in the simplest of questions, infinity may hide.
The Riemann hypothesis is one of the most famous unsolved problems in mathematics. Suggested by Bernhard Riemann in 1859, its main question is simple. Where does a special function become zero? This small question seems to hold a secret about how prime numbers are spread along the number line. Prime numbers are like rare stones scattered along a road. At first, they look random. The Riemann zeta function is like a map that shows subtle hills and valleys where primes appear. When the map hits zero, it marks a quiet point. Riemann guessed that all important zeros lie on a single straight line, the critical line, where the real part equals 1/2. If true, this means the pattern of primes hides a deep order. The zeta function uses complex numbers, which have a real part and an imaginary part. These numbers can seem odd, but they let mathematicians see patterns ordinary numbers hide. Computers have checked many zeros, and they do lie on the critical line so far. Yet no one has proved that all zeros must lie there. A check can show truth for many cases, but it cannot replace a full proof for all cases. Why should we care? Prime numbers are the building blocks of arithmetic, and they matter in real life, like cryptography that keeps online data safe. If the Riemann hypothesis is true, many results about primes would become clearer. If it is false, some tools would change and new surprises would appear. Some physicists noticed that the pattern of zeros looks like energy levels in quantum systems, hinting at a link between numbers and physics. Mathematicians like Hardy, Littlewood, and Turing studied parts of this problem over decades. Their work gave new methods, but not a full solution still. Many brilliant minds have tried to solve this mystery. It is one of the clay millennium problems, with a reward for a correct proof. Yet the reward is small next to the joy of discovery. The Riemann hypothesis teaches patience and shows that simple questions can hide deep truths. The Collatz conjecture is a simple rule about numbers that leads to a strange dance. Start with any whole number. If the number is even, divide it by 2. If the number is odd, multiply it by 3 and add 1. Then repeat the rule over and over with each new number. The question is, will this process always reach the number 1, no matter which starting number you choose? Mathematicians call the sequence a hailstone sequence because the numbers rise and fall like stones tossed in the air. For some numbers, the path is short and calm.
For others, the sequence jumps up and down many times before finally falling back to 1. For example, start with the number 6. It becomes 3, then 10, then 5, then 16, and eventually it reaches 1. Start with 11, and the path becomes longer and wilder before settling down. People have checked the Collatz rule for many numbers using computers, and every number they tried eventually reached 1. But checking many numbers is not the same as proving the rule for all numbers. No one has found a number that does not reach 1, and no one has found a way to prove that none exist. That is why this simple game keeps puzzling minds. The Collatz conjecture is beautiful because it shows how tiny rules can make very complex behavior. A child can understand the rule, but the deep question resists the best efforts of mathematicians. It reminds us that complexity can hide inside what looks like a simple pattern. This mystery connects to bigger ideas. It touches on how we search for patterns, how computers help us explore, and how unpredictability sometimes appears in predictable systems. Some people wonder if the Collatz rule might hide a deep truth about numbers, or if it is simply a clever trick with no deep meaning. Either way, the path it draws feels like a secret river running through the landscape of math.
Infinity is a strange idea. We often think of it as never-ending. But in math, infinity has many faces. Some infinities are larger than others. This can feel like a gentle puzzle that does not stop. Think about the counting numbers: 1, 2, 3, 4, and so on. There are infinitely many of these. We call them the natural numbers. Now, think of all the points on a line between 0 and 1. There are also infinitely many points there. But those two infinities are not the same size. This is one of the first surprises. A mathematician named Georg Cantor showed that the points on a line form a bigger kind of infinity than the counting numbers. He used a clever idea called the diagonal argument. Imagine writing a list of many numbers between 0 and 1. Cantor showed how to make a new number that is not on the list. Change the first digit of the first number, the second of the second, and so on. The new number will differ from every number on the list. That means the line has more points than any list you can write down. It shows math can surprise us and touches deep questions about space and time. You can have a smaller infinity and a larger infinity. You can imagine a hotel with infinite rooms that are all full, yet a new guest can still be given a room. This is called Hilbert's Hotel, and it shows how odd infinite sets can behave. Why does this matter? It shows that math can change our simple ideas about size. It also asks why we trust counting at all when infinity plays by strange rules. If some infinities are bigger, what does that say about the world we live in? Are there realms of thought that are too large to count? This idea feels like a quiet, beautiful paradox that asks us to think slowly and patiently. Take a slow breath and let this mystery settle. Imagine numbers stretching wide like a calm sea, with some waves taller than others. Let the thought rest in your mind without needing a final answer.
The Banach-Tarski paradox is one of the strangest ideas in all of mathematics. It says that if you take a solid ball, like a sphere, and cut it into a small number of special pieces, you can reassemble those pieces into two balls exactly the same size as the original. In other words, you could take one ball, break it apart, and end up with two balls of the same size without stretching or adding anything. At first, this sounds impossible. How can one ball suddenly become two? Doesn't this break the laws of physics? The answer is yes, it breaks the rules of the physical world. But this paradox is not about real objects we can touch. It belongs to pure mathematics, where ideas can behave in ways our everyday world does not allow. The trick comes from a branch of math called set theory, which studies collections of points. The ball in this paradox is made of infinitely many points. The special cuts are not ordinary cuts with scissors or knives. They are abstract divisions that separate the points into strange, unmeasurable sets. Each piece is so unusual that it has no clear volume. That is why, when you put the pieces back together, you can form two whole balls instead of just one. The Banach-Tarski paradox is made possible by something called the axiom of choice, an assumption in mathematics that lets us choose elements from infinitely many sets at once. This axiom is useful in many areas of math, but here it leads to results that feel magical or even unsettling. Of course, you cannot actually do this with a real ball. Atoms cannot be cut in such a way, and the laws of physics prevent it. But as a thought experiment, it shows the difference between the rules of pure math and the rules of the real world. The paradox leaves us with deep questions. What does it mean when math describes things we cannot build? Does this mean math is larger than reality? Or does it show that reality has limits that math does not?
Chaos in mathematics is not just about disorder. It is about systems that follow simple rules but still create results that look random and unpredictable. One small change in the beginning can lead to very different outcomes later. This is often called the butterfly effect. The idea that a butterfly flapping its wings could, in theory, change the path of a storm far away. One of the most famous examples of chaos is the logistic map. This is a simple equation used to describe how populations grow. If you start with a number between 0 and 1 and keep applying, chaos in mathematics is not just about disorder. It is about systems that follow simple rules but still create results that look random and unpredictable. One small change in the beginning can lead to very different outcomes later. This is often called the butterfly effect, the idea that a butterfly flopping its wings could, in theory, change the path of a storm far away. One of the most famous examples of chaos is the logistic map. This is a simple equation used to describe how populations grow. If you start with a number between 0 and 1 and keep applying the rule, the results can behave in surprising ways. For small values, the population settles into a steady balance. For larger values, the numbers start bouncing between 2 values, then 4, then 8, and eventually they seem to jump around without any clear order. From a simple rule comes a world of chaos. Chaos does not mean total randomness. Hidden inside the mess are patterns and shapes. When mathematicians look at chaotic systems, they often find fractals, shapes that repeat themselves at different scales, like the branching of a tree or the edge of a snowflake. These shapes show that chaos has its own kind of beauty, a delicate balance between order and disorder. Why does chaos matter? Because it appears everywhere in real life. Weather, the stock market, traffic, the beating of the human heart, all of these can show chaotic behavior. We can never predict them perfectly because tiny differences in starting points grow into huge differences over time. Chaos teaches us humility, reminding us that even with powerful computers and precise measurements, the future can remain mysterious. At the same time, chaos also offers hope. It shows us that unpredictability can lead to beauty. It suggests that complexity can grow from simple beginnings.
A single equation can produce shapes that look alive, as if nature itself is written in the language of chaos.
Fermat's shadow comes from one of the most famous puzzles in the history of mathematics. In the 1600s, a man named Pierre de Fermat wrote a note in the margin of a book. He claimed he had a wonderful proof that a certain equation had no whole number solutions, but he did not include the proof itself. For centuries, mathematicians tried to solve the puzzle, and it became known as Fermat's last theorem. The equation is simple to state. For whole numbers a, b, and c, the rule a to the n plus b to the n equals c to the n works for n equals 2. This is just the Pythagorean theorem, where 3 squared plus 4 squared equals 5 squared. But Fermat said that for any number higher than 2, like n equals 3, 4, 5, and so on, there are no whole number solutions. In other words, you cannot find 3 whole numbers that fit this rule when the power is greater than 2. The mystery comes from Fermat's note. He wrote, "I have discovered a truly marvelous proof of this, which this margin is too small to contain." But no one ever found his proof. Was he mistaken? Did he really have a proof? Or was it just a passing thought? For more than 300 years, mathematicians searched for the answer. They tried thousands of ideas, proving parts of the problem for certain values, but never for all. The theorem became like a ghost, haunting mathematics, always just out of reach. It inspired generations of thinkers, each chasing Fermat's shadow. Finally, in the 1990s, a mathematician named Andrew Wiles found a proof. It was not short or simple. It used modern tools from areas of math that Fermat could not have known. This made people believe that Fermat's original marvelous proof probably never existed, or at least not in a correct form. Fermat's last theorem is solved now, but its shadow still lingers. It reminds us how a simple note can stir centuries of thought. It shows how human curiosity can keep a question alive far longer than the life of the person who first asked it.
Prime numbers are the building blocks of all whole numbers. They are numbers greater than 1 that can only be divided by 1 and themselves. Examples are 2, 3, 5, 7, 11, and so on. At first glance, primes seem to be scattered randomly along the number line. Sometimes they appear close together, and sometimes there are large gaps between them. The twin prime mystery is about pairs of primes that are only 2 numbers apart, like 11 and 13, or 17 and 19. These pairs are called twin primes. The big question is, are there infinitely many twin primes, or do they eventually stop appearing? So far, mathematicians have found many twin primes, even at very large numbers. For example, there are twin primes in the billions and trillions. This makes us believe they will never run out, but no one has been able to prove it for certain. The idea that there are infinitely many twin primes is called the twin prime conjecture, and it remains one of the most famous unsolved problems in math. Why does this matter? Twin primes show us something deep about the hidden rhythm of prime numbers. Primes are not placed evenly. They get farther apart as numbers grow larger, yet these twin pairs keep showing up, almost like two friends walking side by side through an endless forest. If twin primes do go on forever, it would mean there is more structure to primes than we can currently see. In recent years, progress has been made. In 2013, a mathematician named Yitong Zhang proved that there are infinitely many pairs of primes that are less than 70 million apart. Later, other mathematicians improved this bound to smaller gaps, though not yet down to 2. This shows we are getting closer to the truth, but the mystery remains unsolved. The twin prime problem reminds us of how something so simple, a gap of 2 between primes, can hide such a great mystery. It also shows that math is alive, with questions still waiting in the shadows for answers.
The world we live in feels three-dimensional. We can move left and right, forward and backward, up and down. These 3 directions seem to make up all of space. But mathematicians and scientists often ask, what if there is another direction, one that we cannot see or touch? This is the idea of the 4th dimension. To imagine it, think about a simple story. A flat creature living in a 2-dimensional world, like a drawing on paper, only knows length and width. It cannot look up into the 3rd dimension. If you placed a ball above the paper and lowered it down, the creature would only see a growing and shrinking circle as the ball passed through its flat world. To that creature, the 3rd dimension would be invisible but still real. Now imagine us as the flat creatures, living in 3 dimensions. The 4th dimension might be just as real, but hidden from our senses. If a 4-dimensional object passed through our space, we would only see strange slices of it, changing shape as it moved. For example, a shape called a tesseract is the 4-dimensional version of a cube. If a tesseract passed through our world, we might only see shifting cubes appearing and disappearing. The 4th dimension is not just imagination. In mathematics, it is real and useful. We can describe 4-dimensional shapes with equations. In physics, some theories, like Einstein's relativity, treat time as a kind of 4th dimension combined with space. In other areas of science, higher dimensions are used to model things too complex for 3 dimensions alone. The idea can feel unsettling. What if we're blind to directions that actually exist? What if reality is bigger than we can ever picture? The 4th dimension reminds us that our view of the universe may be only a shadow of something larger. 0 is one of the simplest numbers, yet also one of the most mysterious. It stands for nothing, emptiness, a complete absence. But at the same time, it is one of the most powerful ideas humans have ever created. Without 0, much of modern mathematics and science would not exist. Long ago, many ancient number systems did not have 0. The Romans, for example, used letters like X and V for their numbers, but they had no symbol for nothing. Imagine trying to write large numbers or do complicated calculations without 0. It would be confusing and messy. The invention of 0, which came from ancient India and then spread through the Arab world to Europe, changed everything. 0 gives us a way to mark empty places. In the number 103, the 0 shows there are no tens, but its presence is important. Without it, the meaning of the number would change completely. 0 is also the bridge between positive numbers and negative numbers. It is the point on the number line where positives fall to the right and negatives stretch to the left. Yet 0 brings strange questions. What happens if you try to divide by 0? In math, division means asking how many times one number fits into another. But if you try to divide by 0, the answer makes no sense. This is why dividing by 0 is undefined. It breaks the rules of numbers. 0 also plays a role in calculus, where mathematicians use 0 to understand motion and change. By looking at values as they get closer and closer to 0, they can study things like speed and growth. This shows how nothing can be used to describe something in great detail. The idea of 0 also raises deep, almost philosophical questions. How can nothing become something? Is emptiness itself a kind of presence? In physics, even a vacuum, which seems empty, is filled with energy and activity. Zero teaches us that nothingness is not simple. It is full of hidden meaning.
There is a number in math that seems impossible at first glance. It is the square root of -1. In other words, it is a number that when multiplied by itself gives -1. No ordinary number can do this. If you multiply any positive or negative number by itself, the answer is always positive. This is why mathematicians call this strange new number imaginary. They gave it the symbol I. At first, people thought imaginary numbers were useless. How can something that does not exist help us? But over time, mathematicians discovered that I was not only useful, it was powerful. It opened the door to new horizons in mathematics, physics, and engineering. With imaginary numbers, we can combine the ordinary numbers we know, called real numbers, with I to create complex numbers. A complex number looks like this: A plus BI, where A is a real part, and B is multiplied by I. These numbers may look strange, but they give us a way to describe things that real numbers alone cannot. Complex numbers are used in electricity, signal processing, computer graphics, and even quantum mechanics. They help explain waves, rotations, and vibrations. For example, engineers use them to design radios, phones, and power systems. Without imaginary numbers, much of our modern technology would not exist. Even more mysterious is the beauty that comes from complex numbers. When we explore functions with them, we see incredible fractal patterns, like the famous Mandelbrot set. These shapes are infinite, repeating, and breathtaking, showing the secret art hidden inside math. The name imaginary makes it sound like these numbers are fake, but in truth, they are as real in math as any other number. They remind us that reality is larger than our first impressions. What once seemed impossible becomes a tool to understand the universe.
Some problems are easy to check once you know the answer, but very hard to solve in the first place. This is the heart of the P versus NP problem, one of the biggest open questions in computer science and mathematics. Think about a jigsaw puzzle. If someone shows you the finished picture, it is easy to check that all the pieces fit. But if you only have the loose pieces, finding the right arrangement can take a long time. This difference between checking and solving is what P versus NP is all about. P stands for problems that can be solved quickly by a computer. NP stands for problems where a solution, once given, can be checked quickly, even if finding it is very hard. The mystery is, are these two groups actually the same? In other words, if a problem's answer can be checked easily, can it also be solved easily? Or are there problems that can never be solved quickly, no matter how powerful our computers become? This question matters because many of our modern systems rely on it. Encryption, which protects your messages, passwords, and bank accounts, depends on problems believed to be hard to solve but easy to check. If P turned out to equal NP, many of these protections would fall apart because solving them would become just as easy as checking them. On the other hand, it would also mean breakthroughs in medicine, science, and technology. Many problems that seem impossible today, like designing perfect drugs or optimizing massive systems, might suddenly become simple. Most experts believe that P does not equal NP, meaning there will always be problems that are easy to check but hard to solve. But no one has been able to prove it.
The Clay Mathematics Institute has even offered a $1 million prize for a correct proof. The mystery of P versus NP shows us the limits of knowledge. It reminds us that even with the most powerful tools, some puzzles may remain forever just out of reach.
Randomness feels like pure chance, like flipping a coin, rolling dice, or shuffling cards. We often think of it as unpredictable noise, without pattern or order. But in mathematics, randomness is much harder to define. What does it really mean for something to be truly random? And can we ever prove that something has no hidden pattern? Imagine tossing a coin 100 times. You might expect the results to look messy, with no clear order. But what if you got a perfect sequence like heads, tails, repeating all the way through? It would look suspicious, yet it could still be a possible outcome of random chance. Randomness does not always look random. Sometimes it mimics patterns, sometimes it produces streaks, and sometimes it surprises us. Mathematicians have tried to capture the meaning of randomness with ideas like probability and information theory. One idea says a sequence is random if it cannot be compressed into a shorter rule. For example, the digits 1, 2, 3, 1, 2, 3, 1, 2, 3 can be described with a simple rule: repeat 1, 2, 3. But the digits of a truly random sequence have no shortcut. The only way to describe them is to list them all. This raises deep questions. Is randomness real, or is it just complexity we do not yet understand? In physics, some processes, like radioactive decay, seem truly random. No rule can predict exactly when an atom will break apart. But in other areas, like weather, what looks random may simply be chaos. Patterns too sensitive for us to predict, but not random in the deepest sense. Randomness also plays a big role in computer science. Computers are machines that follow rules, so how can they generate randomness? They use clever tricks, often starting with a number seed and creating sequences that look random but are actually predictable if you know the method. True randomness, like flipping a coin or measuring tiny quantum events, is harder to capture.
Pi, written as the symbol pi, is one of the most famous numbers in the world. It comes from circles. If you take the distance around any circle, the circumference, and divide it by the distance across it, the diameter, you always get the same number, pi. No matter how big or small the circle is, the ratio is always the same. The value of pi starts as 3.14159 and goes on forever without repeating. It is an irrational number, which means it cannot be written as a simple fraction. Its digits never end, and no pattern has ever been found inside them. People have calculated trillions of digits of pi using computers, yet it still keeps stretching into infinity. Pi is more than just about circles. It shows up in unexpected places across mathematics and science. It appears in geometry, trigonometry, calculus, probability, physics, and even in formulas about waves and the motion of planets. It is almost as if pi is woven into the fabric of the universe itself. One of the strangest beauties of pi is how it connects to randomness. If you look at its digits, they seem to behave like random numbers, even though pi is perfectly defined. No one knows for sure if the digits of pi are truly random, but they pass many tests for randomness. It is like finding chaos hidden inside order. Pi also inspires people beyond mathematics. Every year, on March 14th, people celebrate Pi Day because the date 314 looks like the first digits of pi. Students, teachers, and math lovers use the day to enjoy pi, both the food and the number. The mystery of pi is that something so simple, a circle, leads to something so infinite. It reminds us that behind everyday shapes, there are deep secrets waiting to be uncovered.
The golden ratio is a special number that appears again and again in nature, art, and mathematics. It is often written with the Greek letter phi. The value of phi is about 1.618, and it has a unique property. If you take a line, split it into two parts, and the ratio of the whole line to the longer part is the same as the ratio of the longer part to the shorter part, that ratio is the golden ratio. This number has been called the most beautiful ratio. It appears in famous works of art and architecture, like the Parthenon in Greece and Leonardo da Vinci's drawings. Designers often use it because shapes built around this ratio feel balanced and pleasing to the human eye. But the golden ratio is not just about art. It also shows up in nature. Look at the way leaves grow around a stem, or the spiral of shells, or the pattern of seeds in a sunflower. These spirals and arrangements often follow the golden ratio, creating patterns that are both efficient and beautiful. It is as if nature has chosen this number as a quiet rule for growth. In mathematics, phi connects to the Fibonacci sequence, where each number is the sum of the two before it: 1, 1, 2, 3, 5, 8, 13, and so on. As you go further along this sequence, the ratio between two neighboring numbers gets closer and closer to phi. This link between a simple pattern of numbers and the golden ratio shows how deeply it is tied to both growth and balance. The golden ratio also appears in unexpected places, like in music, galaxies, and even in the proportions of the human body. It gives us the sense that mathematics is not only about logic, but also about harmony. Some people believe the golden ratio holds a kind of hidden key to beauty and the universe. Others see it simply as a useful pattern. Either way, it connects math to the world in a way that feels both practical and mysterious.
Not every question in math can be answered. Some equations are not just hard, they are truly unsolvable. This idea can feel strange because we often think of math as a tool that can solve anything if we just try hard enough. But in the 20th century, mathematicians discovered limits to what math can do. One of the most famous examples comes from David Hilbert's list of problems. In 1900, Hilbert challenged the world's mathematicians with 23 deep questions. One of them was about something called Diophantine equations, equations where you want whole number solutions. For example, x squared plus y squared equals z squared has many whole number answers like 3, 4, 5. Hilbert asked if there was a method that could decide whether any Diophantine equation has a solution. Decades later, in the 1970s, the answer came no. Yuri Matiasevich, building on work from other mathematicians, proved that there is no general method. Some Diophantine equations are unsolvable, not because no numbers fit, but because we cannot create a single rule that works for all of them. Each case must be studied on its own. This discovery shook mathematics. It showed that even in the clear world of numbers, there are walls we cannot climb. The dream of finding a universal key to all equations was broken. Instead, we must accept that mystery will always remain. Unsolvable equations connect to ideas in computer science as well. They're linked to undecidable problems, questions that no machine or algorithm can ever fully answer. This means that both humans and computers face limits, no matter how powerful they become. Why does this matter? It humbles us. It shows that mathematics is not a perfect map of truth, but a landscape with shadows and unreachable places. It teaches us that limits can exist
even in the most logical of systems. In the world we see every day, probability is simple. If you flip a coin, there is a 50% chance of heads and a 50% chance of tails. The coin cannot land as both at the same time. But in the strange world of quantum physics, probability works in a way that bends our usual sense of logic. In quantum mechanics, particles like electrons and photons do not have fixed states until we measure them. Instead, they exist in what is called a superposition, many possibilities at once. For example, imagine a coin spinning in the air forever, never landing, showing both heads and tails at the same time. That is close to how quantum states behave. The probability in quantum mechanics does not just come from randomness. It comes from something called a wave function, which is like a cloud of possibilities. This wave function can interfere with itself, like waves in water. Because of this, probabilities in quantum physics can add together, cancel out, or shift in ways that ordinary probability never does. One of the most famous examples is the double-slit experiment. If you fire tiny particles at two slits, they do not behave like little bullets. Instead, they make a pattern of waves, as if each particle goes through both slits at the same time and interferes with itself. Only when you measure the particle, when you look, does it choose a definite path. Until then, it is in a cloud of probabilities. This makes us ask deep questions. Is the universe fundamentally uncertain? Does reality only become real when observed? Albert Einstein disliked this idea. He once said, "God does not play dice with the universe." But experiments show that quantum probabilities are real and cannot be explained away. Quantum probability changes how we think about cause and effect. It suggests that the future is not fully written, only a set of possibilities that collapse when choices are made or when measurements happen.
Long ago, a Greek thinker named Zeno asked questions that seemed simple but turned out to be very confusing. These questions are called Zeno's paradoxes, and they make us wonder about motion, time, and infinity. Even today, they are still discussed because they show how our ideas of the world can break down when we look too closely. One of the most famous paradoxes is called Achilles and the tortoise. Imagine the great runner Achilles racing a slow tortoise. To make it fair, Achilles gives the tortoise a head start. Now, Zeno asks, can Achilles ever catch the tortoise? At first, the answer seems easy. Of course he can. But when we look at it step by step, it becomes strange. First, Achilles must reach the spot where the tortoise began. By then, the tortoise has moved a little farther ahead. Next, Achilles must reach that new spot, but again, the tortoise has moved forward. Every time Achilles reaches where the tortoise was, the tortoise has gone on just a bit more. This seems to go on forever. Does this mean Achilles never catches up? Another paradox is the arrow paradox. Zeno says, at any single instant of time, an arrow in flight is frozen in place. If every moment is like a still picture, then the arrow is always at rest. How can it move at all? These puzzles force us to think about infinity and how we measure motion. The truth is that modern math, with the idea of limits and calculus, shows that Achilles really can pass the tortoise. Adding up an infinite number of steps can still give a finite result. The paradoxes are not unsolvable, but they remind us that infinity behaves in ways that are not natural to our everyday thinking. Zeno's paradoxes are important because they teach us to look deeper at ideas we take for granted. They show how logic can twist our sense of reality and how strange infinity truly is. Imagine a coastline on a map. From far away, it looks like a smooth curve. But if you zoom in, you see bays, rocks, and little curves inside the bigger curve.
Zoom in even more, and you still see smaller curves repeating again and again. This is the idea behind fractals, shapes that show endless detail no matter how close you look. A fractal is a pattern that repeats itself at different scales. One of the most famous examples is the Mandelbrot set. It looks like a black blob with swirls and spirals around it. But when you zoom into its edges, the same shapes appear again and again in new, surprising ways. It feels like falling into an infinite world hidden inside a single picture. Fractals are not just pretty designs. They connect math to the real world. Coastlines, mountains, clouds, trees, even your lungs show fractal-like patterns. Nature seems to use fractals to build complexity out of simple rules. For example, a tree branches into smaller branches, which branch into even smaller ones, until you get leaves and veins. The same rule repeats at many levels. One of the strangest things about fractals is the idea of infinite edges. Take the Koch snowflake, a shape built by starting with a triangle, then adding smaller triangles to each side, then smaller ones again, and again, forever. The shape's perimeter keeps getting longer, approaching infinity, even though the area inside stays finite. This means you can have a shape that fits in a small space but has an endless edge. Fractals challenge our ideas of size and measurement. How long is a coastline? It depends on how closely you measure it. The more detail you include, the longer it gets, and it never truly ends. These patterns are calming and mind-bending at the same time. They show us that infinity is not just an idea, it is something we can see and almost touch in the natural world.
What does it mean to be conscious? To feel, to think, to know that you exist? These questions sound more like philosophy, but some scientists and mathematicians are trying to use math to study consciousness itself. The idea is that maybe the mind follows patterns and rules just like numbers do. One approach is called Integrated Information Theory, or IIT. It tries to measure consciousness as a number. According to this theory, the more connected and integrated the parts of a system are, the more conscious it is. For example, your brain has billions of neurons talking to each other all the time. This creates a huge amount of integration. A light switch, by contrast, has very little. It is just on or off. So, by IIT, your brain has much higher consciousness than a switch. Another idea comes from complexity. Some mathematicians think consciousness arises when a system is complex enough to store and process information about itself. In other words, your mind is like a mirror that can reflect its own image. This self-reference might be the key to awareness. Mathematics also helps us ask deep questions. If consciousness can be measured, could a machine or computer one day reach the same level as a human? Could numbers show us when a robot becomes truly aware? Or is there something about human experience, feelings, thoughts, imagination, that no equation can ever capture? The mathematics of consciousness is still in its early days. No one has found a final formula. But even trying to measure it pushes us closer to understanding what it means to be alive and aware. It mixes logic with mystery, just like so many of the problems we have explored.
Numbers are everywhere in our lives, and most of the time they feel simple. We count apples, we measure time, we add and subtract. But hidden inside the world of numbers is a strange kind called irrational numbers. They are called irrational, not because they are silly, but because they cannot be written as simple fractions. Take the number 2. Its square root, the number which when multiplied by itself equals 2, cannot be written as a fraction like 3/2 or 7/5. Instead, its decimals go on forever without repeating, 1.4142, 135, and so on. This was shocking to the ancient Greeks. Legend says that when one of Pythagoras' followers revealed the discovery of irrational numbers, it caused great upset because it broke the belief that everything in the universe could be explained by whole numbers and simple ratios. Another famous irrational number is pi, which we talked about earlier. It begins 3.14159 and so on, but it never ends and never repeats. Another is e, the base of natural logarithms, which appears in growth, finance, and probability. Irrational numbers live in the cracks between the numbers we can easily write down. They fill the number line completely, making it rich and continuous. In fact, between any two whole numbers, say 4 and 5, there are infinitely many irrational numbers hiding. Why does this matter? Because irrational numbers remind us that the universe is more complicated than it looks. You cannot always trap a truth inside a neat fraction. Sometimes the truth stretches on forever, refusing to be pinned down. This mystery can feel unsettling, but it is also beautiful. It means that even in the quiet simplicity of counting, there is endless depth. The infinite decimals of irrationals are like whispers of infinity hidden in plain sight.
Some numbers are even stranger than irrational numbers. These are called transcendental numbers. Like irrationals, they cannot be written as simple fractions, and their decimals go on forever without repeating. But transcendental numbers are different because they are not the solution to any normal algebraic equation. In other words, you cannot make them by solving something like x squared minus 2 equals 0, 3x plus 5 equals 0. They live beyond algebra in a shadowy place of their own. The most famous transcendental numbers are pi and e. Both of them show up in countless areas of math and science. Pi appears in circles, waves, and even probability. E shows up in growth, interest rates, and the behavior of randomness. Even though they cannot be tied down by simple equations, they somehow control many patterns in the world. The discovery that pi is transcendental was a huge breakthrough in the 1800s. It proved something shocking. You can never make a perfect square with the same area as a perfect circle using only a ruler and compass. This problem, called squaring the circle, had confused people for thousands of years. The answer turned out to be, it's impossible, because pi is transcendental. What makes transcendental numbers so mysterious is how rare they feel and how hard they are to prove. Mathematicians know there are infinitely many of them, so many that, in fact, almost all numbers are transcendental. But proving that a specific number is transcendental is very difficult. Apart from pi and e, only a few are known for sure. The rest remain hidden in the shadows. These numbers remind us that math is not only about order and solutions, but also about limits and mysteries. They sit just out of reach, beyond the usual rules, yet they quietly shape the very structure of reality.
Imagine taking a piece of string and tying it into a knot. Then you glue the ends together so it cannot be undone. Now, you might wonder, is this knot really different from another knot? Can it be untangled without cutting? Or are some knots truly unique? This is the essence of the knot problem in mathematics, a branch called knot theory. Knots are not just for sailors or shoelaces. They are shapes studied in mathematics. A knot is a loop in three-dimensional space that crosses over itself in some way. Mathematicians ask questions like, how can we tell if two knots are the same? Can one be stretched or twisted to look exactly like the other without cutting? Some knots are simple and easy to recognize, while others are complicated and confusing. One tool mathematicians use is called an invariant. This is a property of a knot that stays the same no matter how you twist or stretch it. By comparing invariants, mathematicians can tell if two knots are truly different. This approach has led to many discoveries and even practical applications, like understanding DNA, which can knot and unknot inside cells, affecting how life works. Knots can also be surprisingly beautiful. Some look like braids, spirals, or loops that repeat in intricate patterns. In some ways, they resemble fractals, repeating complexity within a simple loop. Knot theory also connects to physics, helping describe particle interactions and energy fields. The knot problem feels mysterious because a simple loop of string can hide endless complexity. Tiny changes in the way the string crosses itself can create knots that are incredibly difficult to study. Even with modern computers, fully understanding all knots is beyond our reach.
The Poincare Puzzle is about the shape of space itself. Long ago, Henri Poincare asked a simple-sounding question: how can we tell if a three-dimensional space is really a kind of sphere? To explain, imagine the surface of a ball. Any loop you draw on that surface can be tightened until it becomes a single point. Mathematicians call the property simply connected. In 2 dimensions, this idea is easy. Any closed surface without holes that is simply connected is basically a sphere. Poincare wondered if the same was true in 3 dimensions. If a closed 3-dimensional space has the property that every loop can shrink to a point, must that space be a 3-dimensional sphere? The words sound heavy, but the idea is clear. No hidden tunnels, no holes, no strange handles, just a round shape in a deeper sense. This question may seem small, but it turned out to be very deep. 3 dimensions are harder to picture than 2. Our minds can see a flat surface or the skin of a ball, but a 3-sphere lives one step beyond what we can easily imagine. Because of this, mathematicians had to invent new tools to study the shape of space in ways our eyes cannot see. Over many decades, people chipped away at the problem. The breakthrough came from an idea like smoothing. Think of a wrinkled object and imagine heating it so the wrinkles slowly relax. In mathematics, a process called Ricci flow smooths a shape in a similar way. Richard Hamilton developed this method, and Grigori Perelman used it to show that a space with the right properties must become round as it smooths. Perelman completed a proof of the conjecture. His work changed modern geometry forever. It reminds us that simple questions hide deep truth. This result was one of the great moments in modern math. It showed how patient thinking and new tools can solve puzzles that once seemed impossible. Even though the problem is now solved, the story continues to teach us about how math can study shapes that hide from simple sight.
The ABC conjecture is a quiet but deep idea about simple sums. It looks at 3 whole numbers, A, B, and C, that add up like this: A plus B equals C. What makes it special is how it links 2 parts of math, adding and multiplying. It asks if the size of C is usually controlled by the prime factors that appear in A, B, and C. Mathematicians use something called the radical of a number to explain this. The radical takes each prime factor of a number and multiplies those primes once. For example, 72 has prime factors 2 and 3, so the radical is 2 times 3 equals 6. For ABC, we look at the radical of the product A times B times C. This picks out the distinct prime pieces in the equation. The conjecture says, in rough form, that C is not often much larger than the radical of A times B times C. In plain terms, when 2 numbers add to make a third, the third is usually not hugely bigger than the product of all the different primes that appear. Only a few rare sums break this rule. Why is this idea surprising?
Addition and multiplication seem like different games. Adding moves numbers along a line, while multiplying mixes prime parts. ABC links these games in a simple equation. If it is true, many other deep results in number theory would follow quickly. It would help explain why some equations have no solutions, and why some number patterns are rare. One small example shows the strange cases. Take 1 plus 8 equals 9. The product is 1 times 8 times 9 equals 72. And the radical is 2 times 3 equals 6. Here, C is 9, which is larger than 6. Such cases make mathematicians pause and think. In recent years, a claimed proof appeared, but it is very hard to read and check. Many experts studied it, and debate continues. This shows how deep and delicate the ABC idea is. It connects to famous problems like Fermat's last theorem and patterns of primes.
For centuries, people have asked if the universe could be described with just one grand equation. Could all of space, time, matter, and energy be explained by a single line of math? This dream is sometimes called the theory of everything. It is the idea that, deep down, reality is written in the language of numbers and symbols. We already know math works very well for smaller parts of the universe. Newton's equations describe how planets move. Maxwell's equations explain electricity and light. Einstein's equations of relativity describe space and time bending like a fabric. Quantum mechanics uses equations to explain atoms and particles. Each of these is powerful, but they don't all fit together. Relativity works for the very large, and quantum theory works for the very small. But when we try to combine them, the math breaks apart. This is where the dream of one universe equation appears. If such an equation exists, it would unite the rules of the very big and the very small. It would tell us how black holes work, how the universe began, and maybe even why it exists at all. Some scientists search for this in string theory, which imagines tiny vibrating strings as the building blocks of everything. Others look to loop quantum gravity or other bold ideas. But the question is not only scientific, it is also philosophical. If the universe can be written as math, does that mean reality is math? Are we living inside an equation? Or is math only a tool we use, like a map, to understand something much deeper? No one has the answer yet. The search for the equation of the universe is ongoing, and perhaps it will never truly end. But the thought itself is powerful, that all we see, the stars, the oceans, our own thoughts, might be parts of one great pattern.
Prime numbers are the building blocks of all whole numbers. They appear truly simple at first, but many puzzles hide in the spaces between them. One such puzzle is the prime gap problem. A prime gap is the distance between two consecutive prime numbers. Sometimes primes sit side by side, like 11 and 13, which are 2 apart. Other times they are far apart. The question is, how do these gaps grow as numbers get larger? At small sizes, primes can be close or far without a clear rule. But as we move along the number line, the gaps, on average, get longer. This makes sense because primes thin out as numbers grow. Still, their exact pattern feels mysterious. Are there always relatively small gaps? Can gaps become arbitrarily large? How often do small gaps occur among giant numbers? Mathematicians study how prime gaps behave. Some results showed that there are infinitely many gaps of certain sizes, and recent work proved many primes do appear with bounded differences. For example,
researchers found infinitely many pairs of primes within a fixed large gap, and then refined the gap size smaller and smaller. But whether gaps of size 2, called twin primes, occur forever remains open. At the same time, it is known that arbitrarily large gaps do exist. We can find runs of numbers without primes at all, sometimes covering long stretches. This mixture of certainty and mystery makes the prime gap puzzle so interesting. It shows both order and chaos living together. Primes are regular enough to obey deep rules found by mathematicians, yet irregular enough to surprise us often. The puzzle also connects to big ideas like the Riemann Hypothesis. If that hypothesis is true, it would give strong information about how primes are spaced. Why should we care? Prime gaps may seem abstract, but primes matter in many technologies like encryption and coding. Understanding their spacing helps us learn about hidden structure inside numbers. More than that, the prime gap puzzle is a reminder that even simple questions about counting can open doors to deep mysteries.
Imagine a hotel with an infinite number of rooms. This is Hilbert's Infinity Hotel, a thought experiment created by the mathematician David Hilbert. At first, it sounds impossible. How can a hotel have endless rooms? But once you step inside this strange place, infinity begins to play tricks on logic. Picture the hotel. Every room is filled, no vacancies at all. In a normal hotel, that means no one else can check in. But in Hilbert's hotel, infinity changes the rules. If one new guest arrives, the manager simply asks everyone to move. The guest in room 1 goes to room 2. The guest in room 2 goes to room 3, and so on forever. Now room 1 is free, and the new guest has a place. The hotel was full, yet it made space. Now imagine not one guest, but an infinite line of new guests. Strangely, the hotel can still take them in. The manager asks every current guest to move to the room with double their number. Guest 1 goes to room 2, guest 2 goes to room 4, guest 3 goes to room 6, and so on. All the odd-numbered rooms are now empty, an infinite number of them, ready for the infinite new arrivals. This strange hotel shows how infinity breaks our normal thinking. A full hotel can still accept more. A hotel with infinite rooms can even welcome infinite buses filled with infinite guests. Each time, with clever rearrangements, there is always space. The Infinity Hotel raises deep questions. What does it mean for something to be infinite? Is infinity a number, or is it something beyond numbers? In math, infinity is not a place we can reach. It is an idea, a horizon that keeps stretching farther away the closer we approach. Hilbert's hotel is not real, of course, but it helps us see the strange nature of infinite sets. It shows that infinity is not just very large, it has its own rules, rules that often go against common sense.
In the early 1900s, many mathematicians believed that one day math would be complete. They thought that with enough effort, we could write down a set of rules and prove every single true statement in math. Imagine math as a giant puzzle, and they hoped to finally put in the last missing piece. But then, a quiet and brilliant thinker named Kurt Godel came along and changed everything. Godel created what is now called the incompleteness theorems. These ideas are some of the most mind-bending discoveries in logic. To put it simply, Godel proved that no matter how good our system of math is, it will never be able to answer every question. There will always be true statements in math that cannot be proven using the rules of that system. Think of it like this. Imagine writing a book that explains
everything about the universe. No matter how long or detailed that book is, Godel showed that there will always be questions the book cannot answer. It is like trying to hold water in your hands. Some will always slip through your fingers. Godel did this by creating a strange kind of self-referential statement. It's similar to the classic paradox, "This sentence is false." If the sentence is true, then it must be false. If it's false, then it must be true. Godel used math to build a similar statement inside a logical system. The result was shocking. Math could never fully explain itself. The implications are huge. It means that the dream of perfect certainty in math is impossible. No matter how advanced we get, no matter how many rules we create, there will always be mysteries beyond reach. Math, which many people thought of as the most perfect and complete human creation, turned out to be incomplete by its very nature. This makes us ask deep questions. If math is the language of the universe, does that mean the universe itself is filled with truths we can never prove? Are there limits not just to our knowledge, but to knowledge itself?
At first, math seems like it should be clean and perfect. Numbers follow rules, and sets, the groups we make from numbers or objects, feel simple. A set could be all even numbers, or all triangles, or all books on a shelf. Easy, right? But then, in the early 1900s, a philosopher and mathematician named Bertrand Russell found a crack in this simple picture. His discovery is now called Russell's paradox, and it shook the foundations of math and logic. The paradox starts with a simple question: can a set contain itself? Most sets don't. For example, the set of all cats is not a cat. But imagine a special kind of set, the set of all set that do not contain themselves. Does that sound confusing? Let's slow down. Take a library as an example. Some books in the library are about themselves, like a book titled "The Story of This Book." That book refers to itself. Most books, though, are not about themselves. Now, make a shelf with all the books that are not about themselves. Here comes the problem. Should the book titled "The Story of This Shelf" go on that shelf? If it is about itself, then it should not be on the shelf. But if it is not about itself, then it should be on the shelf. Either way, the situation breaks. This is the heart of Russell's paradox. If the set of all sets that do not contain themselves exists, then we are trapped. If the set contains itself, then by definition, it should not contain itself. But if it does not contain itself, then it must contain itself. A logical loop with no way out. The paradox showed that naive set theory, the simple rules people were using at the time to define sets, was flawed. Something so basic, so innocent, turned out to lead to contradictions. This forced mathematicians to rethink the foundations of math. If sets could cause such trouble, then maybe math was not as perfectly safe as people believed. Russell's discovery led to the development of stricter systems of logic and set theory, ones designed to avoid this type of paradox. But the shadow of the paradox still lingers. It reminds us that even in the most precise worlds of math and logic, cracks can appear.
Infinity is strange. We often think of it as one big idea, something that just goes on forever. But in mathematics, infinity is not just one size. There are actually different sizes of infinity. Some infinities are bigger than others. This sounds impossible at first, but it's one of the most fascinating discoveries in math. And at the center of this idea is something called the Continuum Hypothesis. Let's start simple. The smallest infinity comes from the counting numbers, 1, 2, 3, 4, and so on. They never end, so this set is infinite. Mathematicians call this
countable infinity, because even though it is endless, you can still list the numbers one by one. Now, think of all the numbers on the number line between 0 and 1. Not just whole numbers, but decimals too, like 0.1, 0.25, 0.333, 0.47892, and so on. These numbers are called real numbers. Between any two numbers, there are infinitely more numbers. This infinity is much larger than the infinity of counting numbers. It's so large you cannot list them one by one. Here is where the Continuum Hypothesis comes in. It asks, is there a size of infinity that sits between these two sizes? In other words, is there an infinity larger than the counting numbers, but smaller than the infinity of real numbers? This question haunted mathematicians for years. The strange part is that the Continuum Hypothesis can neither be proven true nor false, using the normal rules of math. That means the question lives in a kind of twilight zone, beyond proof. This is both unsettling and beautiful. It shows us that math, which feels like the ultimate source of certainty, also has questions with no definite answers. It stretches the edges of what we mean by truth. Think of infinity as an endless ocean. We can see waves of different sizes, but we don't know if there are secret layers of infinity hidden in the deep. When you look at the world around you, numbers seem to be everywhere. You see 2 hands, 5 fingers on each, 7 days in a week, 12 months in a year. Numbers feel real, like they are part of the universe itself. But here is the strange question. Do numbers actually exist, or are they just ideas in our minds? Some philosophers and mathematicians believe numbers are real things, existing outside of us. This view is called Platonism, after the ancient philosopher Plato. He believed that numbers, like shapes and truths, live in a perfect world of ideas. In this view, the number 3 is not just a symbol we write down, it is something eternal, something that exists whether or not humans are around to notice it. But others say numbers are not real objects. They are inventions, tools that humans created to make sense of the world. Just like we made up words to describe things, we also made up numbers to count, measure, and compare. In this view, if humans disappeared, numbers would vanish too. There would still be trees, stars, and rivers, but no 3 or 10 without minds to label them. This debate goes deep. If numbers are real, then the universe is built on something abstract and eternal. It means math is discovered, not invented, and we are uncovering truths that exist beyond us. But if numbers are human creations, then math is like a language, a brilliant and useful one, but still a product of imagination. Think of it this way. When you see 3 apples on a table, is 3 inside the apples, or is it inside your mind? The apples are real, but the number may just be a way we interpret them. This mystery touches on science too. Physics depends on math, and math depends on numbers. If numbers are real, then maybe math is the blueprint of the universe. If not, then maybe math is just the best tool we've made to describe the world, but not the world itself.
For most of history, people believed there was only one kind of geometry, the one we learn in school called Euclidean geometry. It is based on rules written down by the ancient Greek mathematician Euclid. In this geometry, lines are straight, triangles always add up to 180 degrees, and parallel lines never meet. It feels like common sense, like the way space should work. But then, in the 1800s, mathematicians started to wonder, what if space didn't follow Euclid's rules? What if there were other kinds of geometry? This led to the birth of non-Euclidean geometry, a new way of seeing shapes, lines, and space itself. In one type, called spherical geometry, imagine the surface of a globe. On a globe, the lines are curved, like the equator or the paths of airplanes. Here, parallel lines can actually meet. For example, lines of longitude on a globe start apart at the equator but meet at the North Pole. Triangles on a sphere can add up to more than 180 degrees. The rules we thought were unbreakable suddenly change. In another type, called hyperbolic geometry, space bends the opposite way. Instead of curving like a sphere, it stretches outward like a saddle. Here, triangles add up to less than 180 degrees, and there can be endless lines parallel to each other. At first, people thought this was just a strange math game, but then came a shock. The universe itself might follow non-Euclidean rules. Albert Einstein's theory of general relativity showed that space and time are curved by gravity. Massive objects like stars and black holes bend space around them, making geometry in the universe non-Euclidean. This means the simple, flat geometry we learn as kids is only part of the story. Reality is far stranger and more flexible than our first intuitions. Non-Euclidean geometry opened the door to new ways of thinking, not just in math but in art, science, and philosophy. It showed us that even the most basic truths we assumed about space could be questioned. When you look up at the night sky, it feels endless, like space stretches on forever. But here is the big question. What is the actual shape of the universe? Is it infinite, going on without end, or does it have some kind of boundary? And if it has a boundary, what lies beyond it? These are questions that scientists and mathematicians have wrestled with for centuries. One simple idea is that the universe is flat, like a sheet of paper that extends forever. In this model, the rules of normal geometry apply. Parallel lines never meet, and the angles of a triangle add up to 180 degrees. This kind of universe would be infinite, with no edge, and it fits much of what we see when we study the stars. But there are other possibilities. The universe could be shaped like a sphere. Imagine ants crawling on the surface of a balloon. To the ants, the surface feels endless, but in reality, it curves back on itself. If the universe is like that, you could travel in a straight line forever and eventually return to where you started without ever finding an edge. Another strange idea is that the universe could be shaped like a saddle, curving outward in all directions. In this model, space would stretch infinitely, but the geometry would be very different from the flat universe we picture in our minds. Even stranger possibilities exist too. Some scientists think the universe might have a more complex shape, like a 3D version of a donut, where space loops and twists back on itself in ways that are hard to imagine. The shape of the universe is not just a fun question. It connects to deep ideas about the fate of everything. If the universe is flat or saddle-shaped, it may expand forever. If it is spherical, it might one day stop expanding and collapse back in on itself. To study this, scientists look at the cosmic microwave background, the faint glow left over from the Big Bang. These patterns of light give us clues about the geometry of the universe. Right now, the evidence suggests the universe is very close to flat, but we cannot be sure.
Black holes are some of the most mysterious objects in the universe. They are places where gravity becomes so strong that nothing, not even light, can escape. But behind this mystery lies something surprising. Black holes are deeply connected to mathematics. Numbers and equations tell us how they form, how they grow, and even what secrets they might hide inside. It all begins with Einstein's theory of general relativity. His equations showed that when a star, much bigger than our Sun, runs out of fuel, it can collapse under its own gravity. The math predicts that all the star's mass can shrink into a tiny point called a singularity. Around this point is the event horizon, the invisible boundary of the black hole. Once something crosses this boundary, it can never return. Mathematically, black holes bend space and time itself. Imagine a trampoline with a bowling ball in the middle. The ball makes the fabric dip, and smaller objects roll toward it. A black hole is like this, but far more extreme. The equations describing this bending of space are exact, yet they lead to mind-bending consequences. One strange discovery is that black holes are not just destroyers, they also have temperature and entropy, ideas usually connected to heat and information. The math behind this, developed by Stephen Hawking, shows that black holes can slowly give off energy, known as Hawking radiation. Over immense amounts of time, they might even shrink and disappear. But this leads to one of the biggest puzzles in physics, the information paradox. If things fall into a black hole, is their information lost forever? In normal physics, information cannot simply vanish, but the math of black holes suggests it might. Scientists are still debating this today, and the answer could change how we understand the laws of the universe. Black holes also raise questions about time. Near the edge of a black hole, time slows down compared to the outside world. To someone falling in, things seem normal, but to an outside observer, that person appears frozen at the event horizon.
Entropy is a measure of disorder and a measure of how many ways a thing can be arranged. We see it when ice melts, when a hot drink cools, or when a room becomes messy. The second law of thermodynamics says that total entropy in a closed place usually goes up. That rule helps explain why time seems to move forward. Imagine a tidy desk. Papers are neat, and pens are where they belong. If you wait, the desk will probably get messy. It is much easier for things to fall into disorder than to become neat by themselves. Messy states have many more tiny arrangements than neat ones, so mess is more likely. At a tiny level, particles follow rules that are reversible. If we knew every detail, we could run physics forward or backward. But there are so many particles and tiny details that we cannot track them. Because of this, we see a one-way flow toward more entropy in our daily world. That is why broken eggs do not put themselves back together, and why steam spreads and does not come back to a kettle. A scientist named Ludwig Boltzmann explained entropy using microstates. A microstate is one tiny way particles can be arranged. When there are many microstates for one condition, we call that condition high entropy. Boltzmann wrote an equation that links entropy to how many microstates there are. His idea shows entropy is a statistical idea, not a single fact about one particle. Entropy also connects to information. If we lose details about a system, its entropy goes up. This idea led to deep puzzles about black holes. Black holes seem to hide information about what fell inside, yet they have entropy and even a temperature. Scientists still argue about how information survives or changes near black holes. On a grand scale, entropy makes us think about the fate of the universe. If entropy keeps rising, the universe may move toward a state called heat death, where no useful energy remains and change slows. This idea is quiet and a little unsettling, but it also reminds us of the deep link between order and time.
Grandy's series looks simple at first, but it hides a strange puzzle. The series goes like this: 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1, and so on forever. At first glance, you might think it should just equal 0. After all, if you group the numbers as 1 minus 1 plus 1 minus 1 plus 1 minus 1, the result looks like 0 plus 0 plus 0, which equals 0. But if you group it differently, like 1 plus negative 1 plus 1 plus negative 1 plus 1, the result looks like 1 plus 0 plus 0 plus 0, which equals 1.
So is the series equal to 0 or 1? This is where the confusion begins. Grandy's series does not settle down to one value. Instead, it jumps back and forth between 1 and 0, depending on how many terms you stop at. After the first number, it is 1. After the first 2, it is 0. After 3, it is 1 again. After 4, it is 0. The series does not converge, which means it does not settle to a single number. Yet, mathematicians found a curious trick. If you take the average of the results as the series goes on, you get 1/2. This does not mean the series equals 1/2 in the normal sense. Instead, it means that in certain kinds of mathematics, like Cesaro summation, the series can be treated as if it equals 1/2. This is unsettling because it feels like math is bending its own rules. A series that seems to make no sense is suddenly given a neat answer. But this answer is not wrong. It is useful. The value of 1/2 shows up in physics and engineering, where infinite sums like this sometimes appear in real problems. The puzzle of Grandy's series makes us ask, what does it mean for something infinite to equal a number? Can infinity follow the same rules as ordinary arithmetic, or does it need its own strange logic? In 1963, a mathematician named Stanislaw Ulam was sitting through a long, boring meeting. To pass the time, he started doodling numbers on a piece of paper. He wrote the number 1 in the center, then began placing numbers around it in a spiral. 2 next to 1, 3 next to 2, and so on, curling outward in a square pattern. What seemed like a simple doodle soon turned into one of the strangest discoveries in number theory. As Ulam continued, he noticed something unexpected. When he highlighted all the prime numbers, the numbers that can only be divided by 1 and themselves, they didn't appear scattered randomly across the spiral. Instead, they lined up in beautiful diagonal streaks. Lines of primes seemed to stretch outward from the center, creating hidden patterns across the infinite sea of numbers. This was a shock. Prime numbers have always been known for their unpredictability. They don't follow simple patterns the way even or odd numbers do. But in Ulam's spiral, their arrangement suggested that maybe there are deeper rules hiding beneath the surface, rules we don't yet fully understand. Mathematicians studied Ulam's spiral using computers and found that the diagonal lines appear because certain quadratic equations produce prime numbers more often than others. But still, the patterns are mysterious. No one has proven why primes prefer these diagonal paths, or if the pattern continues forever. Ulam's spiral is a reminder of how math can surprise us. Something as ordinary as writing numbers in a spiral can reveal hidden beauty in the structure of the universe. It also shows how patterns can appear in chaos, giving us hints that there may be secrets about primes still waiting to be uncovered. Probability feels simple. It is the math of chance, the study of how likely something is to happen. Flip a coin, and there's a 50-50 chance of heads or tails. Roll a die, and each side has a 1 in 6 chance. But when we look closer, probability can twist into paradoxes that leave us scratching our heads. One of the most famous is the Monty Hall problem. Imagine a game show. There are 3 doors. Behind one door is a car, and behind the other 2 are goats. You pick a door, hoping for the car. Before you open it, the host, who knows where the car is, opens one of the other doors to reveal a goat. Now you must decide. Should you stay with your first choice or switch to the other unopened door? Most people think it doesn't matter. It feels like a 50-50 chance. But math says switching doubles your chance of winning. If you stick with your first choice, your chance is 1 in 3.
If you switch, your chance is 2 in 3. This result feels wrong to many people, but experiments prove it is true. Another paradox is the birthday problem. In a room of just 23 people, there's about a 50% chance that 2 people share the same birthday. With 70 people, the chance jumps to 99%. Our intuition fails because we think about our own birthday, not about all the possible pairs of people in the group. Then there's the gambler's fallacy. Imagine flipping a coin and getting heads 5 times in a row. Many people think tails is now due to appear. But each flip is independent. The chance of tails is still 50%. The coin has no memory. These paradoxes show how human intuition often struggles with probability. We expect chance to feel fair and balanced, but randomness doesn't work the way we imagine. Probability paradoxes remind us that chance can be both surprising and mysterious. They also matter in real life, from medical tests to financial decisions to understanding risks.
At first glance, the harmonic series looks harmless. It begins very simply. 1 plus half plus 1/3 plus 1/4 plus 1/5 plus 1/6 and so on forever. Each new term is just the reciprocal of a whole number. The numbers get smaller and smaller as we go on. 1/10 is small, 1/100th is tiny, and 1/1000th is almost nothing. You might think that if you keep adding smaller and smaller numbers, the total should eventually settle down to some limit. But here is the strange truth. It doesn't. The harmonic series grows without bound. Mathematicians say it diverges. That means if you keep adding terms forever, the sum becomes infinitely large. This feels impossible at first. How can adding such tiny fractions like 1/1,000,000th make the total blow up to infinity? But that's exactly what happens, though very slowly. To see why, let's group the terms. Start with 1, 1/2, 1/3 plus 1/4, 1/5 plus 1/6 plus 1/7 plus 1/8, 1/9 plus up to 1/16. Notice something? Each group adds up to at least 1/2. The third group is bigger than 1/2. The fourth is also bigger than 1/2, and so on. Since you can keep forming groups forever, you keep adding 1/2 again and again. This shows that the sum must grow without end. The harmonic series is more than just a curious math trick. It appears everywhere, in music, in physics, in engineering, even in the internet's structure. The word harmonic itself comes from music, because the overtones of a vibrating string follow the same pattern. 1, 1/2, 1/3, 1/4, 1/5, and so on. These overtones create harmony. But the series is also tied to randomness, probability, and even prime numbers. For example, the distribution of prime numbers is deeply connected to the behavior of the harmonic series. What makes it mysterious is the way it grows. It doesn't race off to infinity quickly. It creeps there, almost like it's sneaking upward when no one is watching. Even after 1,000,000 terms, the total is only around 14. But no matter how far you go, it never stops rising. This teaches us a strange lesson. Even the tiniest things, when added together endlessly, can become unbounded. Small differences, repeated enough times, can create something enormous.
Music may sound like pure emotion, but beneath every note lies mathematics. When a string on a guitar vibrates, or when you sing a note, what you're really hearing is a wave. That wave has a frequency, how many times it repeats each second. The higher the frequency, the higher the pitch. The lower the frequency, the deeper the sound. Now here's the magical part. Many of the most beautiful sounds we hear are tied to simple fractions. If one string vibrates twice as fast as another, they form an octave. That's why a C note on the piano sounds so similar to the next higher C. Their frequencies are in a 2-to-1 ratio. Other pleasing sounds, like a perfect fifth, happen when the ratio is 3-to-2. A perfect fourth comes from 4-to-3. These simple fractions are the reason music feels harmonious. The human ear loves order, and these ratios create it naturally. Long ago, Pythagoras discovered this by stretching strings and plucking them. He noticed that shorter strings gave higher pitches, and the simple ratios made sweet music. But not all music is so simple. Western music uses 12 notes in a scale, and they don't all fit neatly into perfect fractions. To make instruments like pianos work, musicians use something called equal temperament. This system slightly adjusts the notes so that all 12 fit into an octave evenly. The math behind this uses powers of the 12th root of 2, a number that cannot be expressed as a simple fraction. This tiny adjustment allows songs to shift between keys without sounding out of tune. Without it, many modern pieces would not be possible. Music also shapes rhythm. Beats are divided into halves, quarters, eighths, again fractions. Even complex rhythms like jazz or polyrhythms can be broken down into mathematical patterns. When drummers overlay a rhythm of 3 beats against 4 beats, it creates tension and release, all from simple numbers. And if you look deeper, music itself is waves adding together just like equations. That's why computers can record and play music. They're just storing numbers that describe the waves. So next time you hear a song, think of the hidden numbers inside. Every note, every beat, every harmony is built on math.
Between the endless march of numbers, there are spaces, little silences we call gaps. When we look at prime numbers, for example, they seem to pop up at random. 2, 3, 5, 7, 11. Then suddenly a bigger pause before the next one. These pauses are the gaps, and they hold some of the deepest mysteries in mathematics. At first, the gaps between primes are small. Between 2 and 3, there's no gap at all, just one step. But as numbers grow larger, the gaps start to stretch. Sometimes you find primes close together, like 17 and 19, called twin primes. Other times, the silence feels longer, with big stretches of numbers that have no primes at all. Mathematicians wonder, do these gaps ever stop growing? Or is there a pattern hidden inside them? The strange thing is, even though prime numbers are so important, they're like the atoms of mathematics, we still don't fully understand the rhythm of their gaps. One famous question is whether there are infinitely many twin primes. Do primes continue to appear side by side forever, no matter how far we count? Many believe the answer is yes, but no proof has been found. Another mystery is how large the gaps can get. We know they grow, but do they grow without limit? The gaps between primes almost feel like silence in music, unexpected pauses that make the notes more powerful when they arrive. Without silence, music is just noise. Without gaps, numbers would lose their mystery. The space itself seems to hold meaning. Some researchers use computers to study prime gaps, searching into trillions of digits. They find strange patterns, yet the complete truth remains hidden, like whispers we can't quite catch. These silences in the number line remind us that mystery is not only in what we see, but in what we don't. The missing, the waiting, the spaces in between all shape the story just as much as the numbers themselves.
In nature, we see symmetry everywhere. A butterfly's wings, the petals of a flower, the snowflake's design, all show balance and order. But mathematics takes symmetry far beyond what we can see with our eyes. At the very top of this hidden world is something called the monster group, also known as monstrous symmetry. The monster group is not a creature, though the name makes it sound that way. It is a gigantic mathematical object, so large and complex that it almost feels alive. Imagine symmetry so vast that it has more than 196,000 dimensions. We live in just 3 dimensions, up and down, left and right, forward and backward. Now imagine a shape that needs almost 200,000 directions to describe it. That is the size of the monster. The monster group belongs to a special family called finite simple groups. These are like the basic building blocks of symmetry, the way atoms are the building blocks of matter. For centuries, mathematicians searched for all possible simple groups. When they finally finished the list, the monster stood out as the largest, most mysterious of them all. What makes it so fascinating is that the monster is connected to many unexpected areas of math and physics. In the 1970s, mathematicians found a strange link between the monster and string theory, the idea that the universe is made up of tiny vibrating strings. This surprising connection became known as monstrous moonshine. It was as if the monster, born from pure math, secretly matched the structure of the universe. Even today, no one fully understands why such a huge and complicated symmetry exists or why it appears in so many different areas. It feels like the monster is whispering a truth about reality that we haven't yet decoded. The beauty of the monster lies not in being practical, but in showing us that mathematics can uncover hidden worlds stranger than any dream. It is a reminder that even in the deepest layers of numbers, we find patterns too vast to imagine.
Some mysteries in math are not about one single problem, but about a giant web that ties many problems together. The Langlands Program is one of these webs. Some people even call it a grand unified theory of mathematics. It tries to connect areas of math that seem very far apart, like number theory, which studies the secrets of numbers, and geometry, which studies shapes. The idea began in the late 1960s with a mathematician named Robert Langlands. He sent a letter to another famous mathematician, André Weil, sharing a wild idea. What if equations about numbers could be linked to equations about symmetry and shapes? At first, it sounded almost impossible, but over time, his idea grew into one of the deepest projects in modern math. Here's one way to think about it. Imagine you're holding 2 very different books. One book is about prime numbers, the other about curved surfaces and shapes. The Langlands Program says these 2 books are secretly telling the same story, just in different languages. If you can translate between them, you can solve problems that seemed impossible before. One example is Fermat's last theorem, which we talked about earlier. For hundreds of years, nobody could prove it, but in the 1990s, Andrew Wiles solved it by using tools inspired by the Langlands Program. His work showed how connecting different parts of math could crack even the hardest puzzles. The Langlands Program is still far from complete. Mathematicians around the world are working on it, often devoting their entire careers to just one corner of the web. Some call it a mathematical Everest, because climbing it takes huge effort, but reaching the top could give a view of the whole landscape of mathematics. What makes it so mysterious is that we don't know why these deep connections exist. Why should prime numbers, the most basic things in math, have anything to do with shapes and symmetry? It feels like the universe is built with a hidden code, and the Langlands Program is helping us see pieces of it.
Imagine you write a computer program. You press run, and now you wait. Will it finish and give you an answer, or will it keep going forever, stuck in a loop? This question seems simple, but it hides one of the deepest problems in computer science, the halting problem. The halting problem asks, is there a perfect method, a master program, that can look at any program and decide whether it will stop or run forever? At first, you might think, of course there should be. Just analyze the code, check the logic, and you'll know. But in 1936, a young mathematician named Alan Turing showed that no such master program can exist. Turing's proof works like a clever puzzle. He imagined, suppose we did have a program, let's call it H, that could check any other program and predict if it halts or not. Then he built a strange new program that asks H about itself. If H says, this program halts, the program forces itself to run forever. If H says, this program runs forever, the program forces itself to stop. In both cases, H gets it wrong. This contradiction proves that such a perfect program can never exist. The halting problem is not just a trick, it has big meaning. It shows there are limits to what computers and even mathematics itself can do. Some questions can never be answered by an algorithm, no matter how powerful our machines become. This doesn't mean we can't solve specific cases. For many programs, we can test and see. But there will always be some cases where the truth hides beyond our reach. The halting problem also touches on philosophy. If computers can't predict all outcomes, then even machines face uncertainty. It reminds us that the world of logic and numbers, which feels so solid, has built-in mysteries that cannot be removed.
The human mind feels like the most mysterious thing in the universe. It thinks, dreams, remembers, and wonders. But can something so rich and alive be described by mathematics? Many scientists and philosophers believe it can, or at least that math can give us clues about how the mind works. One way math enters the mind is through patterns. Your brain is full of billions of neurons, tiny cells that pass signals to each other. Each neuron can either fire or stay quiet, much like the ones and zeros inside a computer. When many neurons work together, they form networks that process information. Mathematicians study these networks with equations, trying to understand how thoughts, memories, or even emotions might appear from simple signals. Probability also plays a big role. The brain does not always work in strict yes or no answers. Instead, it often deals with chances. For example, when you walk in the dark and hear a sound, your brain quickly calculates the odds. Was that the wind or something else? It weighs the possibilities, almost like running math silently in the background. Another fascinating idea is that the mind might compress information. Just like a computer shrinks a large file into a smaller one, your brain takes the endless stream of sights, sounds, and feelings and reduces them into simple models. This might be why you can look at a tree filled with millions of leaves and still instantly know that is a tree. Mathematics of information theory helps explain how the brain can do this. But there are also mysteries that math has not solved. Can consciousness, the feeling of being aware, really be measured by numbers? Some theories say yes, that awareness is the result of complexity and connections. Others say no, that human experience is beyond equations. The mathematics of the mind is still young, but it gives us a new way of asking old questions. What makes us who we are? How do thoughts appear? Can machines ever think like us?
Some sentences refuse to tell the truth. Try this. This sentence is false. If the sentence is true, then it must be false. If it is false, then it must be true. This is the liar's paradox. It is a loop that traps meaning inside its own words. Mathematicians found similar loops with numbers. Imagine you try to list every number that can be described in a short sentence. Then ask, What is the smallest number that cannot be described in less than 20 words? This idea is the Berry paradox. If the number can be described that way, then it is not supposed to be describable. The sentence creates a contradiction, like the liar's sentence. Kurt Godel used this trick but turned it into something deep and precise. He showed how to turn statements into numbers. Then a number can stand for a sentence about math. Godel built a number that encodes a sentence saying, "This statement cannot be proved." If the sentence can be proved, a contradiction appears. If it cannot be proved, then it is a true statement that cannot be proved. This idea leads to incompleteness. Some true things in math cannot be proven inside a system. These self-referential tricks also appear in computing. The halting problem is similar. Asking if a program will stop when given itself as input creates a loop that cannot be resolved. Self-reference can make systems ask about their own behavior in ways they cannot answer. There are also definable and undefinable numbers. Many numbers can be named or described by a short rule, but most numbers cannot. If you try to name the first number not nameable in 10 words, you run into trouble. The act of naming changes the meaning, and the paradox appears again. Why do these puzzles matter? They show the edges of what math and logic can do. They teach us to be careful with words and definitions. They force mathematicians to rethink foundations, leading to new rules that avoid some contradictions. Yet self-reference still finds ways to surprise us.
For centuries, scientists and dreamers have wondered if there could be one simple equation that explains everything. This idea is called the ultimate equation. It is the thought that beneath all the laws of nature, gravity, light, atoms, and space, there might be a single, beautiful formula that binds them together. We already use many powerful equations. Newton's laws tell how planets move. Maxwell's equations explain light and electricity. Einstein's equations describe gravity and curved space. Quantum equations describe atoms and particles. Each works well in its place, but when we try to join them, the math often breaks. The ultimate equation is a dream that would unite these laws. If we found it, we could understand black holes, the start of the universe, and how particles and space relate. Some hope string theory might be that equation, with tiny vibrating strings making particles. Others try different paths. So far, the dream remains a search, not an answer. Why chase this idea? Partly because it feels beautiful. A single rule that explains many things would be elegant. Partly because it could solve hard questions and give new predictions. And partly because humans like unity, the sense that many parts come from one pattern. But we must be careful. Nature might not have one simple law. Many laws could work together in complex ways. Also, some questions may be limited and cannot be answered. Perhaps the ultimate equation is missing not because we are not clever, but because nature does not give a single key. The search teaches us how to think. It shows how to build ideas, test them, and stay humble when truth hides. It asks us to balance hope and caution and stay open to new thought.
We have traveled through many quiet questions tonight. Each one opened like a small door. Some doors led to bright rooms of knowledge. Some opened onto dark halls that still hold answers. These doors show the world is larger than any single mind. A math problem can be like a poem. It can be simple and hard at the same time. You can hold it in your hands and still feel its edges reach into the unknown. When a question stays unanswered, it is not a failure. It is an invitation to wonder, to learn, and to rest in not knowing. Think of a lake at night. The surface is still. Light moves across it in soft ripples.
Each question is like a stone dropped into that lake. The ripples spread farther than you can see. You might never find the stone's origin, yet the ripples are beautiful, and they change the water in gentle ways. Some truths can be proved, and some we sense but cannot prove. Some rules fit, and some bend. Sometimes math gives a clear answer. Sometimes it offers a quiet hint. Both are useful. Both are kind. The hint lets the mind breathe. Through history, many people stood at these doors. Some studied for a lifetime. Some left notes to guide others. The work of many hearts and minds passes from hand to hand. That shows how small we are and how connected. We join a slow conversation, bigger than any single life. It is okay to be curious and calm at the same time. You can hold questions gently. Carry them like a small lamp that lights a path, not a weight that must be solved tonight. Let curiosity be soft. Let it be a companion for sleeping or waking. If you are tired, rest. The world will wait. The questions will stay. They are patient. Some will be answered by future minds. Some may never be answered at all. That does not make them less lovely. It makes them mysterious.